Okay, hello everyone. I will start sharing my screen. I think you can see it. Okay, so this will be our final lecture, and practically the only new thing that we will learn today is about, let's say, using computing clusters. So if you remember in the beginning, we said that high performance computing is meant to be done on supercomputers, on computing clusters, and so on. So it's actually, let's say, not meant for us to run very high performance simulations on our regular laptop or desktop computers. We can do it, of course, in let's say in smaller amounts with smaller problems, just to test our programs. But once we have developed our code, we can upload it to supercomputer or computing cluster, and then run the full simulation with more data and maybe with uh, some larger problems in total. Um, so how this is usually done? The computing cluster, I don't know if I have mentioned it. It's actually, let's say, a collection of computers. Uh, Multiple processors are connected using uh, sometimes infinity band cables or whichever. So multiple processors are connected and they can be used together. Usually, once you get the access to your from your company or from research facility or whatever, you will acquire the address of your of that computing cluster. You will get your username and your password. And for that, you will usually need some form of SSH client. So SSH stands for Secure Shell. That's a network protocol for connecting usually to server or to any other computer or device. And the terminal will open once you connect. So here I have a few sessions already remembered. I'm not sure which one, let's say this one, whichever. So for this, I entered medflow.biorc.ac.rs into the here, remove host. Then I specified my username, and after that, I entered my password. But here I had my password remembered, and something like this will open. So this is a terminal, and this here is actually another protocol. It is called SFTP. Secure File Transfer Protocol. All of these that I'm mentioning are part of computer networking, so it doesn't have much to do with high performance computing. It is part of computer networking, but it is useful to have maybe some basic knowledge of this if you ever have the chance to work with computing clusters. It will be easier for you, I think, if you already saw something. So it will probably be a bit different for you, but it should be similar. And here on computing cluster, on this one, PBS is used. PBS, I think I have already provided you with PBS script. Yeah, is this one. So this is a portable patch system that PBS stands for portable patch system. And here you can see some basic commands. This qsub is used to submit a job. So once you write your your program, you will write a script that goes something like this. So this is a subscript, and you will use this script to run your program. So what you're using, you're giving this PBS job a name, and here it is called Eratosthenes based on our Eratosthenes sieve, if you remember that code, but it doesn't matter, it can be whichever. Then this line is always the same, we are using the batch. Just a second, let me check. Yeah, okay. Then we are specifying the number of nodes that we can use. So the node is actually one component of computing cluster, and it is a node has one or more processors, and cluster has many computing nodes. So here we can specify that number of nodes. Then maybe we can load some modules. Here module OpenMPI is loaded. This is a model within which the MPI library is installed. Then we are changing the rights for so we can execute the programs within our directory, and then we are running the program. So we are here using npi run instead of npi exec because this is another operating system. What I have shown you before, it was all under the Windows operating system, but for this computing cluster, for example, it is operating system is Linux Scientific, so it's not Windows. And here npi run is used instead. Here we are not specifying, if you remember, minus np and then the number of processes. That shouldn't be mentioned here because we are already specifying the number of nodes that we want this program to be executed on. Okay. And then you would use this, you would say qsub and then the name of this script, and your job will be submitted to the scheduling system of the computing cluster. So you're using qsub and then the name. I think I have already shown this, but I think it is good to mention it once again. You can see all the other jobs that are submitted by other users. So here you can see some examples. These are chemists. They are not computer scientists, but they are running molecular simulations, which require a lot of computing resources. And with this, you can see more details. If you say qstat -an, you can see the nodes. So these are the nodes, node date. Then you see the processors within these nodes that are being used. So this program is using 12 processors. Okay, some of them are using 8, some of them are using 4, some of them 16, and so on. Okay, another one is show queue, and here you can see the status. You can see which ones are running, which ones are executing, and you can see the ones that are being idle. Maybe they are waiting, they're in a queue waiting to be executed. And then you have blocked jobs. Maybe if somebody is if some job is has some mistake, it will go to a blocked list. Okay, if you want to delete your job, you will use qdel and then this number, the number of course I won't stop this process because I shouldn't stop it, it's from somebody else. But you would be using qdel and then the number of your job to stop the job. So it's not the same as we are doing it in local. Of course, you could go to another directory using cd command. This command will print your current working directory. It is short for print working directory. That's why it is called like this. And if you want to go to, let's say, here, then you would do something like this. You would say change directory, cd, and then the name of the directory. And maybe here you could run some of the some of your programs using npi run. You can do that, but it is not recommended because then you are, let's say, disturbing the scheduling system with your you're using the resources on a non-typical way for computing cluster. So typical way of using computing cluster is by writing a subscript, then submitting your job. If then you either wait for your results, or maybe if you want to stop your program, you would call qdel and then delete your then stop the execution of your program. I here just deleted something that I don't want it to be here. For that I used command remove. You don't have to know these commands, but maybe it's okay if you see it. Okay, so maybe just a quick recap. We are using SSH connection to connect to computing cluster. Then we can upload our script here. It's very simple by using this button. Once we upload the script, we run it using qsub and then the name of the script. And after that, we can check on our program using qstat, and we can delete it if we want. Of course, don't forget to navigate through your file system using cd command. When you see this cd and then ... that means go to the directory that is directly above this one. So above directory Bogdan, it's this directory, this home directory. Okay, here it is used for to clear the screen. So I think that's it about connection to computing cluster. Once again, computing cluster is just a collection of processors that are connected. Maybe something more, I just remember. If you want to see the process specification, you could use ls CPU. That's to list the CPU. And here you have some specification. This is pretty old processor, so yeah, but it's okay. Here you can see the number of CPUs. So this node has 16 CPUs, and there are maybe around 20 nodes here. Some of them are not working. So in total, this once had around 300 processors, but now it has a little bit less. This is pretty old computing cluster. So. Okay. I had here a GPU station, but it's not here now. For machine learning, commonly GPUs are used. GPU stands for graphical processing unit. Maybe I can find something here. I don't think so. And when you are talking about machine learning, you will be mostly using CUDA-enabled GPUs, which can be programmed. Just a second. Oh. I can't access maybe like this. Okay. And these are commonly used to train the neural networks. To write a CUDA program, you will be actually using multi-threaded programming. So you will not create processes as we did with NPI. You would create threads. If you remember our first class, thread is kind of a lightweight process. Threads have shared memory within the process, and processes have distributed memory that are not shared. So we have, let's say, one process, we have some other process, and within a process we can have a few threads maybe. So these threads can be executed in parallel, but they usually have some form of shared memory within this process, and they can have some form of local memory. And for GPUs, you will actually be using many threads, because GPUs are very different from CPUs. GPUs have a lot of cores, really a lot of cores. So processors usually have, I don't know, some have 4, some have 8 cores, but GPUs have thousands of cores. Each of the core is slower than one standard CPU, central processing unit core. So this is processor, central processing unit, and GPU is graphical processing unit. Okay. Now let's put something like this. CUDA threads. And as I said, we have many cores. And we can, even though these cores are slower than core within a processor, central processing unit, as you can see here. So this is CPU and it has few cores, and then GPU has many cores. They are slower than these cores, but there are many of them, and they're suitable for programs where you have let's say high throughput, where you have many operations that can be done independently. For example, once you're processing matrices, you can use GPUs to process GPU's cores to process parts of matrices, or many matrices, maybe multiplication or something like that, in parallel. So many at once. Here we could do, let's say, 4 at once, but here we can do many at once, and this can be faster. Even though one single core is slower than this core, in total this could be a lot faster than just simply using CPU. And the reason why it is very useful for training neural networks is because matrix multiplication is very common operation, for example, during the training of neural network, also during the inference, during the prediction phase, but it is especially useful during the training. The threads on GPUs are executed within these blocks, actually within grids, and then within grids we have blocks, and grids can be 1D grids, so just like imagine it like a line, that's one-dimensional grid, then two-dimensional grid, and it can be also executed within three-dimensional grids. And here each grid has a block. Here it is a 3D block, if you can see. And then within block, we organize the threads. Okay, so we have grids, and within grids blocks, and then threads are being executed there. And so there will be many threads that are processing parts of our program execution. So actually, this CUDA-enabled GPUs, they are using global memory, they're using shared memory and local memory. I mean, by that I mean local memory of a thread, shared memory between threads, and we can also have global memory. And what you're usually doing here is parts of your program will be executed on CPU, so on central processing unit. But then you will move memory, some part of memory, to GPU, which has less memory than your main memory, of course. Then process it, store the result, and then give it back to central processing unit. So this is how the computation is usually going. You're moving the data to a graphical processing unit, then you're processing it, and then moving back to central processing unit. On this course, we won't be writing such programs, but I think you should get some sense of it. Sorry. And maybe for CUDA for now, it's just enough for you to know about that, to know that GPUs exist, to know that you should use CUDA-enabled GPUs. So that's not probably the GPU that you have at home. And most likely, once you obtain the access to GPU, you will connect to it in a similar way that I connected to a computing cluster. So that's pretty similar. Or you could use, I don't know if you use this on another course, but you could use Google Colab. Google Colabs are, they offer the usage of some their resources, and you can choose to, let's say, train your neural network on a GPU or on TPU. TPU stands for Tensor Processing Unit. Me personally, I have been mostly using GPUs. For me, they were fast enough, but TPUs are also specialized to train the neural networks. Okay, let me just think if I forgot to say something. Maybe I should have mentioned to train the neural network on a CPU when you have a lot of data, it can maybe last for several weeks even. And that same training on GPU would last maybe just a few days. So you will save a lot of time if you are using GPU to train your neural network, for example. Of course, the training can last for several weeks even in GPU if you have a lot of data, but nevertheless on CPU it would last a lot more. I don't know which courses you have already listened to, but you have probably heard about batch size when training the neural network. If you haven't, it's just the amount of data that is being processed at once during the training, and you're usually specifying some number that is a power of 2, maybe 512 or 256, so some number that is a power of 2. And the reason for this is because the data is better organized if you're using a power 2. You could actually use any number, but the reason for this power of 2 is that the data is easily organized within these blocks or cores of a GPU if you put a number of if you put a number that is a power of 2 for batch size. So for when you have a larger batch size, more data can be processed at once. Maybe you have millions of data, and then you put batch size around 1,000. And you could increase it. Of course, you have to also watch for other hyperparameters of your neural network. Not to mess too much on them, you have to adjust, of course, also the learning rate if you're changing the batch size. But you could increase that batch size, especially if you're using GPUs, in order to have faster training. For CPU, if you increase your batch size too much, it won't help a lot, because the CPU, Central Processing Unit, doesn't have a lot of cores. GPUs have, so you could increase your batch size. Of course, you can't increase it to a huge number, but I think it really depends on the type of the data that you're using, but the common values are somewhere around 1,000, around 2,000, and so on. So it's actually 1,024 or 2,048, because those two are the powers of 2. Okay, so I think that's pretty much about GPUs. For this, you should, if you want to implement something for GPUs, you would usually be using C++ and CUDA libraries. There are specialized CUDA libraries, for example, CUDNN for deep learning. This DNN is short for deep neural networks. So for this, you will be most probably be using C, C++, and CUDA libraries. When training neural network, it is not necessary to have this knowledge of CUDA programming, because most of the things are already written for you. TensorFlow, if you have been using that, is usually easily installed to be executed on CUDA-enabled GPUs, and you just simply run the same program that you have been running on CPU. You will be running the same program, the same code for a GPU. Maybe some smaller changes. With neural networks, you can also use more GPUs at once. If you have an environment where more GPUs are available, you could train your neural network in parallel at 2 or more graphical processing units in order to speed the training up. To speed up the training. Okay. So that's about CUDA. Another thing that we won't be doing in this class, but maybe you can research it if you want, or maybe you will get in touch with it somewhere along your career. It's OpenNP. So we have been using NPI, or there are a lot of implementations of NPI. For example, OpenNPI. That's one implementation of message passing interface. But there is another thing very similar, and that's why I'm mentioning it. OpenNP without the I, and this I it's just one letter difference, but it's actually totally the same, totally different thing. OpenNP, I'll Google it here, is actually a library, let's say, for multi-threaded programming. Okay. Maybe I can. Is there some image? Not really. And some programs. So this is again with message passing interface or with MPI, we are writing a code that is used to be executed on multiple processors, or in total, let's say that is used to run many processes. Okay, for MPI, OpenMP, it's usually a single process, but with many threads. So similar to how we are doing the CUDA programming, we are running many threads at once, not processes, but threads. Here with OpenMPI, we are doing something similar, but it is done for CPU, for Central Processing Unit. And of course, you can combine these two approaches. You can use approach where you have many processes, and within each of the processes, you have threads. So the main difference between threads and processes, I would say, is the way in how you're managing your memory. For processes, each of the processes have their own memory. If you remember our codes, we had one matrix in one process, another part of matrix in another process, and so on. With threads, usually some parts of memory are shared. So they're accessing actually the same matrix. If you have, with MPI, if you have multiple processes and they all have the same matrix, I mean the same values in the matrix, those matrices are stored in another place, in another physical place. They have the same values, but are stored, let me draw something. So if you have one process, another process, and they have, for example, this process loaded a matrix, and then it shared it with this one, and they have the same values. They have the same matrix, let's say. I mean, in the sense that these are the same values. But this is duplicated. One matrix is here, another matrix is here with a second process. For threads, that's not the case. If they are usually, if some data is common, they will usually be sharing it. And this can cause additional problems, because if you're sharing the same memory, if this thread wants to write here, and maybe this one wants to read, or even worse, to write somewhere the same, they have to do it synchronously. Okay, they have to do it in such a way that the result is the same as if they executed one after another in a sequential manner. So this is why when you have multi-threaded cores, this is sometimes called concurrent programming, because they are accessing the same part of memory. And when you have multiple processes, this is called parallel programming. So these two are two different things. Write it. And I might have misspelled this word, but I think it has two R's. It doesn't matter. Okay, so this is threads, and this is processes, and you can combine these two approaches. For example, MPI and CUDA are often combined together, so you could write a program where you have MPI to execute your program on multiple CPUs, but also you can, each of those CPUs could have access to GPUs, and then you will also be writing a portion of your code for CUDA, for GPU. So portion of your code will be might be a CUDA program in CUDA enabled GPU. Okay, so we have been working mostly with MPI. I have mentioned to you CUDA-enabled programming, so programming for GPUs. I have also mentioned for OpenMPI. Both of these are using multi-threaded or concurrent programming. With CUDA, it's a little bit different. CUDA is often mentioned in a context of parallel computing, even though there are multiple threads. That's because GPUs have really a large number of cores, and usually this is used for tasks that are massively parallel. When you have many repeated operations, maybe small operations, but they are repeated for a large number of data. So CUDA is really often mentioned in the context of parallel computing, and don't let that confuse you, even though you would be using and you are using threads for this. Okay, let's go back and maybe go through some of the codes that we have been written using MPI. And on your exams, I'm not still sure how exactly the exam will be organized. I think it will be mostly seminar papers, but I'm still not sure. So I will let you know by email. But you will be expected only to use MPI and not these things that I have mentioned. I mentioned this only so you have maybe awareness that not only the MPI is used for high performance computing, but also some other things. And if you want, you can go and look into them. Okay. No. I might need this more. So now we are going just to recap everything, to help you to summarize everything, to help you maybe more easily prepare for your exams. So in the first class, we just reminded ourselves of basic Python programming, and then we went through introduction to parallelization in Python using NPI. We have been working with point-to-point communications and with collective communications. For example, when we want one process to send the data to everybody else, we learned that it is better to use collective communication, that is called broadcast, which is efficiently implemented. And point-to-point communication is more typically used when you have those non-blocking calls, for example, or if you want just to send the data from one process to another, you should be using point-to-point communications. Okay. Then we talked about different types of decomposition. We talked about cyclic decomposition, and we talked about domain decomposition. These two terms are very important. So cyclic decomposition is first one, and the second is domain decomposition. Difference between them is just how you decompose the data. So if you have the data and you have your processes, if you are decomposing data in a cyclic manner, in such a way that first process 1 is processing, process 0 is processing the data, then process 1, then process 2, and then again process 0, process 1, process 2, and then somewhere again process 0, process 1, process 2, and so on until the end. So that is cyclic decomposition. Maybe just like say this process 1 element of array, then the next one is being processed by process 1, the next element by process 2, and so on. So this is cyclic decomposition because the processes are being cycled along the data. Domain decomposition is where you have specific domains associated with a process. So let's say first portion of a domain is associated with process 0, and the next portion is associated with process 1, and final with the next process or process. Of course, there can be many processes. I'm just using an example where we are having 3 processes, but we could have as many as we want. Okay, so cyclic decomposition, domain decomposition. And with cyclic decomposition, if you remember, I think we have maybe written 1 or 2 programs, and then we have been mostly using the domain decomposition. With domain decomposition, difficult thing was when we have the amounts of data, let's say n, which is not strictly divisible by the number of processes. For example, if you have 10 portions of data, but you have 3 processes, 2 of the processes should work, let's say, with 3 portions of data, and maybe the last one or anyone will be working with 4. So the data is not totally equally distributed among the processes, but should be distributed the most evenly as possible. For example, if you had 11, it's not fair for this one to work with 5 portions of data and for this one to work with 3. It is better for 2 of the processes to work with 4. Okay? And then we have a total of 11. So once again, cyclic decomposition in the upper part of the screen, and in the lower part of the screen, domain decomposition. So these are things that you should remember. And I mean, that's pretty much it. You should go through all of this, and you have some additional presentations. I don't expect you to read through all of these books. If you want, you can, but it is not necessary. Maybe just go through these PDF files, and you will have, I have here more programs than are uploaded online. For example, you are missing this one. That's okay, just skip it. So we haven't done this. We did some basic examples. We did matrix vector multiplication yesterday, and we demonstrated more complicated scatterby and non-blocking functions. We have also written these, if you remember, so you should look also into that. And with this sieve parallel, so that's the Eratosthenes sieve, you should only look into the domain decomposition part. You don't have to go into the full logic of the code. Okay. I think we can finish in maybe 15 minutes. It depends. Do you have maybe some questions for me now? It's okay if not. So maybe for now, I'll just remind you of few programs. No, I'm still not sure, honestly. Because I haven't sent you the actual topic on your seminar, so I'm not sure what the deadline would be. I think it won't be a large seminar, so once I send you this the topic, maybe around 2 weeks to finish it, but it won't be a large seminar paper. So your seminar paper should contain the following, maybe to mention that. The introduction, just to describe the topic, what is it, what's the problem statement, and so on. Then after that, you should write about methodology, so about MPI functions, just a few paragraphs about high performance computing. And then after methodology, you will have your code should also be within this section, so within the methodology section. And then the next two sections, results and conclusions. Results. For results, you're expected to run your program with different amount of processes, okay? If you remember, I think I have done this with maybe with C or I think with Monte Carlo. It doesn't matter. For any program, it is the same. So you would run your program with, let's say, 2, 5, and 10 processes, and see and perform the analysis. Which one executed the fastest? Which one executed the slowest? Maybe you should also change the amount of data that is being processed. Okay. So it will be necessary for you to perform the analysis. To write your code, you can use ChatGPT. That's okay. I don't mind. And I will try to let's say, simplify the task so that it won't be difficult for you and and ChatGPT to write it, but you should be able to run the programs and to perform the analysis. So that's the let's say main task for you, not the actual programming, because I think it can be a difficult thing to do if you don't have a lot of background in it. But to perform the analysis, to say this program executes faster when you run it with 5 processes, and it has a total of this amount of data. And also, what would also be good is for you to write down which processor you have been using, okay? Because it won't be the same. The results won't be the same if you're using some processor with larger number of cores. For example, all of these that I have been executing in front of you are ran on the following processor. Just a second. It's a good question. So this is the processor that I have been using for to execute our programs. So you should specify this too. Okay. Just go to your file manager, then go to this PC, and then right click and properties. And this should be written in your seminar paper, because as I told you, it really depends on the number of cores that your processor has. Okay. And of course of sorry. You could also run task manager, just type it in, you could also run, sorry, a task manager, just type it in the starting menu line. And once you execute your program, you could also check this. Maybe just take a screenshot of this. Okay. So here you also have the GPU. As you can see, I'm not using the NVIDIA GPUs. Only the NVIDIA GPUs are CUDA enabled, so this is not CUDA enabled GPU. You can't train your neural network on this GPU. I'm losing a lot of memory for some reason. Well, it's okay. Here you also see the number of cores, or for my computer it is 4, and the number of logical processors is 8. So it kind of makes sense to run my MPI programs on 8 cores, not on more than that, because I mean on I should run 8 processes with my MPI programs. With more than that, we are not expecting to see any speed up, because only 8 at the same time can be executed. So if you remember one of the classes, for me usually, if there was a speed up at all with larger number of processor, then it was somewhere between 4 and 8 usually. Okay. So you can take a screenshot of this once you're running your programs. Not maybe I should run something. Let's run, I don't know. Let's run Monte Carlo. That's okay. I think we have been running that one. Let's run it with 4 processes. Oh, sorry. NPI exec is here. Then name of Python. Oh. I should activate my environment to be HPC, because within the HPC I have installed NPI 4Pi. As you can see here, HPC is activated, and then I will run it on 4 processes. Oh, once again this mistake. Let's change this. Let's put just the ID. Okay. And as you can see now that my CPU usage has increased, okay, because I'm running I'm running 4 processes that are actually using a lot of CPU. They're calculating a lot. And I can even hear my CPU. Hopefully you can, but as you can see here, it is used a lot. And then maybe towards the end of the execution, the percentage will decrease. So currently it is around 80% of users. So you should take a screenshot of this too once you're writing your assignment. I will probably give you a topic maybe next week. So next week I will send you by email the topic of your seminar papers, and then you should finish them maybe by 10th of January or 15th of January. So somewhere between. Okay. I also maybe wanted to go once again through some of the codes, but I'm not sure if it's useful for you. I mean, if you understood everything, which I have been saying to you in the previous classes, then maybe we don't need to go through codes once again. But if you want, I can. So, maybe, what do you think? Would you like to go through codes again, or maybe through some of them that I think are important? So let's go once again to Monte Carlo Collective, through with a the sum in point-to-point communications, and I'd like to see one that is maybe one is that we did yesterday. So only these three codes. You should go through all of the ones that are available online. I think you have the link. Let me check. Sorry. So everything that you need is here, and maybe a little bit more. These books you can go through, but you don't have to. Here, yeah, here you have everything you need, including this subscript that you can't run on your computer, but everything else you should be able to run. This is just a help file, so it's really short. Everything else is Python code, but these two aren't, of course. Okay. So these are the codes that you need to study and to understand. And based on these codes, you should be able to program something that's for your seminar with the help of GPT. Maybe I will put some part of seminar to be a little bit more complicated in a from programming perspective. But the core part of it will be pretty straightforward in order for everyone to manage to do it. Okay, so let's check the ones that I've selected. And let's first go through this one, sum, then to Monte Carlo, and finally, once again, to matrix vector multiplication, and I think that should be it for this course. So what's always important, we will always have these three when we are dealing with NPI. The communicator, which is a default communicator that contains all of the processes. We'll have our rank, and we'll have the number of processes that are being executed. Here, once again, it is important for you to note that the number of processor is determined at an execution time. So once we run the program, we know how many processes there are. Okay, the user specifies. I mean, in this case, we are our user, but we can specify different amounts of processes here. Okay, for the same code. So the same code is being used, is being written in a way that you can run it on a single process, you can run it as two processes, three, and so on, as many as you would like, or as many as your computer can handle. Okay, so these three. This rank will be different for each of the process, and usually we are dividing our code in such a way that we are saying zeroed process or everyone else. Usually the data is with the zeroed process. Either the zero process reads it from some file, or it creates it, and then it distributes it to all the other. Maybe it, to everyone else. Maybe it broadcasts the data, so everyone has everything. Maybe it scatters the data, so everyone has a portion of data. In this case, it kind of broadcasted the data, but not using the collective function, using point-to-point function send. And that's here. Maybe just comment this one. So here we created the data, only if we are a zero process. Then we determine the size of everyone's chunk, so a portion of data. And then if we are zero process, we calculated the indices for everyone. For this, we used cyclic decomposition, and cyclic decomposition you can see here. So we are using the indices starting from I all the way until the end of the array, which is of size n, and every time we are skipping what amounts of data, the number of processes amount of data. Okay, so in this case that's the size. So this is the starting index, and for everyone it is actually their rank. Okay. Process with rank 0 will start from 0 portion of data. Process with rank 1 from first, process with rank 2 from second, and so on, all the way until the end, but everyone will skip the number of of processes, that many units. How large this number is, this amount of data will be skipped by everyone. So in the end, what we have this. Process 0 starts here, then skips the number of process source, this amount of data, and then it skips and goes to this. He, process 0, or it, skips the number of processors data and then goes through this, and all the way until then. So everyone is doing the same thing. These indices here are specified only by the zeroth process. The zeroth process then takes the chunk of the data using those indices. It is storing it if it is for him or for it, maybe better to say it, and it is sending that chunk for everybody else. So please note this loop. This is done for each. This is loop through processes. This I here resembles the ID of a process. Okay, so zeroth process prepared the chunks for everybody, and it sent the data to everybody. So this is the destination, the ith process. To whom it only didn't send to itself, because it is the zeroth process. This is done by zeroth process, and by everybody else only expects the data from the zeroth process, so it is receiving the data in their own chunk. Everybody is doing the same thing. They are summing the data, and once they sum the data, they should send back their partial results to through process 0. So this is that part. So we are sending our partial result to who? To process 0, and then process 0 is going through a loop through all of the processes. It is receiving data from them, and it is accumulating the data using it is receiving the data and is accumulating the data. All of this can be replaced with a single reduce, if you remember, because this is a reduction operation. And not only that it can be replaced, it is more efficient, because this is point-to-point communication where each process is sending their portion of data back to one process. I will sketch this once again, because I think it. So if this is zeroth process, and we are having, let's say, few more, process 1, process 2, process 3, process 4, so in total 5 processes. If everybody is sending data to process 0, this cannot be processed at the same time. So this will be first thing, this will be second, third, and fourth. So in this case, the communication executed in 4 steps. There is a much more efficient way to do this. So this here is how it was implemented in our first program, using point-to-point communications, using send and receive. Using a reduction operation for collective communication, we could send data, let's say, like this, from P1 to P2 and at the same time from P4 to P3. These two can be done independently. Okay, his P4 is sending and P1 is sending, P3 is receiving and P2 is receiving. Okay, so let's say this is a first step. Then maybe in next step he sends the data to process 2. So that is the second step, and third step maybe something like this. So this is more efficient. If you remember, the efficiency of this is logarithm with the base 2, and then here we have the number of processes. This number is smaller than this number, and this number is number of processes minus 1. If you remember mathematics, this number is 2 to which power gives mt. So if we are having 8 processes, 2 to which power gives 8? It is 3. 2 times 2 times 2 gives 8. So for example, if the number of processes is 8, with point-to-point communications implemented like this, we would have 7 communication steps. Okay, the number of processes minus 1. This is of course larger than 2 to which power gives 8. In this case that's 3, because 2, I will write it here in a bracket, 2 to the power of 3 gives 8. Okay. And maybe if we had, let's say, 16, the number of communication steps in this case would be 15, and then for this it will be 2 to the power of 4. So it's 4 steps, sorry. Logarithm with base 2 of 16 is 4. Of course, if we are having 17 processes, it will be 17 minus 1, so it's 16. But here, 2 to which power gives 17, we have to look at the first larger number than 17. We can say 2 to the power 4, because that's 16, that's less. But we could use 2 to the power of 5, so the next power. 2 to the power of 5 is 32, but that's okay, 32 is larger than 17. So it's actually the first power of 2 that is greater or equal than the number of processes. So in this case, it will be performed in 5 steps. So this is, of course, a lot faster than 16. This is also the reduction operation or broadcast operation and so on. They're all implemented in the background using the send and receive, but just not in this way, not in a way that everybody is sending at a different time, but some communications can be done in parallel at the same time. Okay, so that's about this first one. So with Monte Carlo, we got a bit smarter here, and we actually used the reduction operation. So what we did here, we calculated the number of points, if you remember, that are within the circle, and their number of points in total. But so each process generated their own random values, and they counted the number of points that are within the circle, that are inside. And then everybody sent to the zeroth process their amount of points that are inside. So everybody is sending to a root process. They are sending what? They're sending their amount of points that are inside. And all of this should be added together. So NPI sum is being used. Okay? So this is the number of points that are inside. This is the name of the reduction operation that is being performed. So reduction here is actually just we could say aggregation of multiple values into a single one. It could be the summation of a lot of values. It could be the minimization, finding the minimal value of all of many values. So once again, we are from multiple values. We are just using one. We are saying what's the smallest number here. We are aggregating many values into one. So that's reduction here. This and this is pretty much the same thing. The same thing happens. Everybody is sending the data to the zeroth process, and it is accumulating all the data. It is performing the summation. The same thing happens here, but it's just in a single line, plus it is more efficient than what it is written here. Okay, and then just the zeroth process calculated the final amount and printed it on the screen. So this is kind of a domain decomposition. This was cyclic. This was, let's say, domain decomposition, but this is actually so parallel that it didn't need a decomposition at all. Everybody is generating their own random values. If this is a total amount of random values, then everybody is generating this amount of random values. And here we didn't care if this is divisible or not, because there is not much difference if we created 1000 points or 1001 random point. Random point is pretty much a random point. We should have a lot of them. The more we have, the more precision we will get in the pi number. But it really doesn't matter if we don't create 2 or 3 more or less. Okay. But we could say this is kind of a domain decomposition. Everybody has their own domain. And here it was also domain decomposition. So this is the one that we did yesterday, and this is the simplest one. Is the matrix and vector multiplication. Let me just check if the program finished. No, still no. Oh, so it finished. Okay. So this is the how much it took. It took a lot. And maybe let's run the same one, but with 8 processes. So that's this one actually. But this number is quite large. This is the total number of points that is being generated. So it is taking some time. This should be faster, we'll see. So with 4 processes, it was this many seconds. And we got pretty good precision. This is okay. This is a difference between pi number with 25 correct decimal points, and then this is hour. So difference between these two is this much, with relatively small difference. So we are getting a good precision of pi number. Okay, let's go to this task. So here, I would like to emphasize one thing. We are using the array split. And if you remember from yesterday, for example, when we had 5 rows, let's say here 5, one of the processes should get 3 rows and the other should get 2. So it's not totally the same amount, but in total they should make up 5 rows. And maybe you would think here that you should use scatter B, because the process 0, for example, should have 3 amounts of data or 3 rows, and process 1 should have 2. But the way that this split is working, it's actually creating a new matrix of only 2 elements. Okay? The first element is being 3 rows. The second element is 2 rows. Okay? But everybody is getting 1 element from this this variable. It's a little bit maybe weird, but just how this data is stored when you call the array split. one portion of data in one split, the second portion in second split, and so on. Okay? So you can use here actually that's kind of convenient in Python. In C, for example, you would most probably be using scatter v for this kind of problem. Okay, so here we splitted the matrix into size parts, where size is the number of processes, and then we scatter the data to everybody else. We broadcast the vector, and they are performing the multiplication. So sequential version of this code is just this line, but parallel version. First, we are scattering the data and broadcasting. Okay, we are scattering the matrix because we are dividing it into components, and we are broadcasting the full vector. Then everybody is doing their multiplication, and then we are gathering back the results and printing it on, merging it, and finally printing it on screen. Okay, I don't think I have changed anything. Oh, yeah, I changed it to 5. Okay. I think this would last probably a few more minutes. Are there maybe more questions from your side now? So seminar, please don't know, expect it by the end of this year, probably next week. Everybody will get topic. Maybe I will. I don't know how many of you know each other. I'm thinking if it's good to maybe organize you in groups. Not sure. Maybe it's better if everyone has their own topic. And you should write, I don't know, 10 pages is enough, maybe even less. You can do more if you want, but maybe, let's say, from 5 till 20 pages. But you don't need to write a lot. It is okay to be concise. Just perform this type of analysis, run the programs, and check the execution time. Don't forget, when you write your code, to perform the analysis, you will need this. I forgot to mention it. So you will need the function MPI ptime that measures the current time, okay? So you can store the current time of your program, for example, before before calculations, let's say. And then at the end of your program, once all the calculation is done, you should also call for that was on here the same function, and then just to subtract these two values to check how much time it took for the program to execute this part, to run the calculation. Okay, so this is important only for your analysis. Once again, you should also check this. So maybe if you're using maybe more processes, maybe more memory is used, maybe less. Maybe you're using a lot of your CPU as I'm doing right now, or maybe you're using a little bit less. So you should take a screenshot of this, maybe even a few times if you want, during your program execution. I don't think we have to wait for this. If you want, I can email you the amount of time that it took for my computer to run this with 4 and with 8 processes, just if you're curious enough. But it doesn't matter. I think we can finish for today, and then next week I will contact you by email and tell you your topic, or maybe two smaller topics for this subject. And that's the bit. How is exam organized in other subjects? Maybe you can tell me that if you want. Is it the same like seminar papers, or are you having some tests, or if you want, I can repeat. If you don't know, or if you're not ready yet, we can talk about it some other time. I think we can finish for today. So once again, during next week, I will probably contact you and tell you your topics. If you want to change your topic, that's also okay. Maybe if it's too difficult to you or not interesting for you or whatever, you can ask me for another one. But please do it um, as soon as possible. Don't wait until the deadline uh, to tell me that you want to change the topic. So yeah. Okay. So I think we have finished our today's lecture, and hear from you by email, or if you want some consultations, we can organize that too. Okay. Bye.
Goodbye. Thank you for the lecture.
Bye. Yes, you can. I think I have already sent you something. You don't have. This is my email. If you have any questions about any lectures or whatever, you can write to. Goodbye.